internal energy plus small kinetic energy plus potential energy. All I did was just here normalize it by the mass, which we're already talking about specific quantity. So based on this, if I go and substitute this in here, what do I get? I get my substantial derivative again, and it's the integral of my control volume over time, rho, my specific internal energy, or my specific total energy is equal to the summation of Q dot net plus W dot net. And that's the general form of the equation. So from there, I could just decompose it and start doing my Reynolds transfer theorem. So let's apply Reynolds transfer theorem. And what am I going to get? I'm going to get d over dt of my control volume, rho total energy over volume, is equal to minus the integral of my control surface, rho, my internal energy, that's our total energy, multiplied by the velocity. So I decomposed it into mass, ds. So my control surface plus the rate of change, or the total summation of my Q net plus my W net. So same thing that we've been talking so far. Take this Reynolds transfer theorem, which fixes my volume, and look at what goes in and out in terms of control surface. So let's decompose the work and the heat. So work and heat, let's expand those. So consider work first. What am I used to in work in general? I would say W net is equal to, or the summation of W net is equal to W shaft plus W boundary, some boundary work, plus W body. And we said, well, neglect. We said fluid is light enough that I don't have to worry about its mass, so I'm not going to take that into consideration. But again, it depends on the problem. I'm lining it up so you know when to introduce it if you're dealing with a heavy base fluid. If you could get rust out of water. Boundary work. What type of form of boundary work? Well, think of the piston. I have some boundary here. I add Q in to my control volume. What's going to happen? Gas is going to expand. Piston is going to move up. I get boundary work. Let's see. So my boundary work is equal to the integral of my volume 2 relative to volume 1, the pressure, because it's constant, over the rate of change of volume. And this is a quasi equilibrium process. Okay, so how does this relate to my propulsion system? So this is, okay, pistons, I understand pistons, it's a moving boundary, so I understand that. How do I go and do it for an aero engine? Well, think of the aero engine as the same principle. If I have some flow that is coming in to a control volume that I'm defining, what that flow is like, and if I take that control volume and draw it again, this right here is my control volume, and this section right here, I'm going to isolate it and highlight it right here. So it's a area volume of fluid that I'm defining coming at a specific velocity to that control volume, and it's just rams in there, and it goes into that domain, inside that control volume domain, and by doing that, it's the same principle as, oh sorry, it's low. Okay, so control volume, fluid coming in. I'm going to outline that specific volume of fluid that's coming into my control volume. Think of it as a propulsion system. This is my inlet. As it rams in, that is the boundary work. And it's the same principle as a piston, because it's the rate of change of that. So we could say that D work is equal to pressure of, if we say, in this case, it's work in, right? I'm doing work in onto the fluid, so work in, pressure in, dV in, and I can decompose that into pressure in, since this is volume. I can say it's delta I in divided by rho in, and that's equal to dI, since I have mass, I can just say V of dMi. And I can say, well, I want to take a look at the rate of that, because it's dot. So dt is equal to dI and dI dMi dt, and that is equal to dI dI mI. And the same thing you can do about work out. You can say if it's a workout, then it's pressure multiplied by the velocity of fluid. Oh, sorry, this out. Out. And that's it. Oh, sure, sorry. So from there, the same principle we could apply for the heat, and we could put it back into our original equation, which is this right here.
Even dt there.
This right here. Well, we applied Brown's transfer theorem, so we want to decompose those terms. So let's write it in terms of these two terms. Now, keeping in mind that we know the definition of enthalpy, so I could just say, based on those two equations, and rewrite them. Keep this up. I could just say work is equal to minus my control surface integration P V rho velocity, normal component velocity ds. So I'm just decomposing it into what goes in versus what goes out. Have it ends out there. So from there, we can also use enthalpy. So we could convert our temperatures. Enthalpy is equal to the internal energy plus PV. So first law, you could say the general form of it is, let me put the other equation up. Here. So this equation right here, I just want to decompose all the terms so I can apply it to a propulsion system. So I'll say d over dt, the integral of my control volume, rho multiplied by my internal energy, times the volume, is equal to minus the integral of rho. Now I have enthalpy, so it will be, I'm going to substitute enthalpy in there instead of internal energy. So it will be enthalpy plus kinetic energy plus potential energy multiplied by velocity, normal component, ds, plus your Q in net and work net. So if I say steady state, this term will go to 0, and say 1D, my general form of the equation, that's the one I want you to get used to, Q net plus m dot net is equal, or plus, yeah, move everything on one side so I can make it equal to 0. Plus the summation of the inlets, which is m dot by enthalpy, kinetic energy, plus potential energy, minus the summation of outlets, m dot outlet multiplied by enthalpy, plus kinetic energy, plus potential energy, outlet, this is inlet, is going to equal to 0. This is steady state. And all this is just the decomposition of this term right here. This term right here. I just want to see what comes around. I've got a question.
What does that curly V represent?
It's just volume.
Volume?
Yeah. Specific volume.
Specific volume.
Yes. So based on that, we got a generic form of our energy equation. And we can start applying it based on the enthalpy, kinetic energy, and potential energy. And depending on your system in general, you might not have potential energy to deal with. You might have the kinetic energy, which you get from momentum equation. However, this is the general form of the energy equation. And you just already know heat is going to come from the system that we're going to induce here through heat of formation and reaction. Work is your shaft work in a propulsion system, so you just have to account for it. If you have a turbine or a compressor that is inducing or taking away work, so your turbine is taking away work from the flow, so we have to account for it, and I will show you how we're going to compute this. This we're going to have to do through chemical reactions. But the important thing is we want to look at the rate of change in energy, which is right here. Again, think of how we got to this. Right? We started with total energy, rate of change of total energy. This is what I have. I need to decompose that term. I took it through my substantial derivative and decomposed it into a Reynolds transfer theorem. So I have my unsteady term and what goes in versus what goes out. So the unsteady term, you could just say, I don't want to deal with a lot of terms, so I'm going to take it 0 for now. Look at what goes in versus what goes out, relative to the total energy. The total energy is internal energy plus kinetic energy plus potential energy. Now, we know that we're going to have enthalpy right here. We know that enthalpy is equal to the internal energy plus your PV. So PV is your work essentially that is being done. So I can compose primarily the total energy that I have of the system right here. Again, specific total energy, which is equal to your specific internal energy and specific kinetic energy or potential energy. Relating this to my enthalpy, so I can track enthalpy changes, and I end up with essentially mass times enthalpy, kinetic energy, potential energy, what comes in minus what goes out, plus the rate of change of the system. We'll do examples on it, and it'll be clearer as we keep tracking it. However, this assumes, and that one of the flaws of the first law specifically is it could work either way, meaning that I could
simply go from a cold system to a hot system, a hot system to a cold system with no restrictions. And I'll show examples of this as well, which is not valid.
So that's where the second law of thermo would apply. So second law of thermo. So I have processes that the second law says, well, I have a reversible system, irreversible system, and I have an impossible system. So, meaning that if I have T hot and I'm inducing some Q in, let's say, to some heat engine of some sort, the expectation is I'm gonna always get workout. But is it 100% workout? No. So that's where it's not specifically possible to do this. There is losses. So this is possible.
What does it say in the first box?
Reversible.
Why?
Reversible,
Because I am gonna have a heat out. Not
T
all
hot,
the
T
energy
hot.
is gonna be taken from whatever system that is inducing